Okay. Good morning, everybody, to today's Taos seminar. It's a pleasure to welcome today's speaker, Dr. Jan Perlwitz. Perlwitz. And he has currently a shared position at Columbia University in the Department of Applied Physics and Applied Mathematics, and at NASA Goddard Institute for Space Sciences. Briefly, from where he is originally, like me, from Germany. I learned that only lately. He did his diploma or bachelor degree in physics math at the Humboldt University in Berlin. Did his master's in meteorology then, also at the Humboldt University in Berlin. But then for his PhD, he was at the Max Planck Institute for Meteorology in Hamburg. And then, of course, the Max Planck Institute cannot give a PhD title. That is in association with the University of Hamburg. And then afterwards, he came to Columbia University and is their senior research associate since then. And his expertise is in climate modeling, in particular implementing aerosol particles into climate models, and we cross paths because, as we learned today, he is an expert for detailed mineralogical representation in models, and mineral dust is a good ice nuclei, and somehow then we cross paths about that. And so you're curious to learn more about that today, and we thank you being here, and welcome again.
The introduction, and thanks for having me. So I'm going to talk about predicting the mineral composition of dust aerosols and a little bit about implications for ice-forming nuclei. And I would like to credit my co-authors, Carlos Perez Garcia Pando and Ron Miller. Without them, I couldn't have done this work. And also, I would like to credit Anne Friedland with GIS and Daniel for the input for the ice nucleation part. I could not have done this part without Daniel's comments. And so on the title slide, you see a satellite photo which displays a dust cloud that's coming off the coast of North Africa, and that is already related to the talk. You can see that it has two distinctive colors. One is grayish and one is reddish, and the grayish dust, that is dust which has a low iron oxide content, and the reddish dust is dust with a high iron oxide content. So I like this satellite photo very much, so I'm always showing it. I'm going to talk a little bit first about soil dust in the Earth system, a small introduction, then why is the mineral composition of dust important. Then I'm going to introduce our approach to simulate prognostic minerals in the model. We also did some evaluation of our simulations of the results, about which I'm going to talk, also as evidence that our approach is superior compared to a more simple approach. And I'm going to talk about preliminary results on my first attempt on ice nucleation, and a little bit about the grand plan, what we are planning to do with the prognostic minerals in the model. And I conclude with a summary. So soil dust aerosols are a major aerosol in the atmosphere. The global emission is about 1,000 to, is estimated to be 1,000 to more than 6,500 teragram a year, and the total mass load in the atmosphere is estimated to be approximately 15 to 35 teragram. You already can see that there's actually high uncertainty about how much dust is emitted in the Earth system and how much dust is in the atmosphere. Dust as aerosol has a high spatial and temporal variability. The dust particle size range is from about 0.1 to 500 micrometers particle diameter. It is important because it absorbs and reflects radiation It has therefore an impact on the radiation balance. It can have both a warming or cooling effect depending on the single scattering albedo of the dust particles. It also can act as cloud condensation nuclei. At least some dust minerals can, probably. And as ice, and it's very important as ice forming nuclei. It plays a role in atmospheric chemistry. There are heterogeneous chemical reactions taking place on the surface of the dust particles. Trace gases, there's an uptake of trace gases which influences the trace gas budget in the atmosphere, and indirectly also the load and fluxes of other aerosols. Then dust is also important as carrier of nutrients like iron, which is important for the fertilization of phytoplankton in the oceans, which in turn is important for modulating the carbon cycle in the atmosphere. Or phosphorus is also a carrier of phosphorus, which is important for the terrestrial biosphere, for instance, the Amazon. So this is an scanning electron microscope picture for different dust particle types. You can see that they come in different shapes and also sizes. And we have, for instance, a quartz particle in the upper left panel. I don't know whether you can see the size. It's about 10 micrometers. This is about, so the quartz particle has a size of about 20 micrometers. Then this is a clay particle in the form of plate. This is a cluster or an aggregate of many clay particles. This is diatom shell, or this, maybe I don't explain everything. This is a carbonaceous particle, and this is I think that's clay, yeah, with a coating of sulfates. So here I show a distribution of the different dust sources. So dust is emitted in deserts and semi-arid regions. The major dust source is the Sahel, and Saudi Arabian Peninsula, and then there's an important dust sources also Central Asia and East Asia. Smaller dust sources are being found in North America, South America, Southern Africa, and in Australia. I'm not going to go into details about all the different dust sources. I rather would like to show an example of a dust source. And this is a photo I took when I went to the Middle East in February, and the plane was flying nearly parallel to the Nile River basin, and it was very nice, was impressive to see that. So we have the Nile oasis here, and adjacent we have the deserts. And when I looked a little bit closer, so that's not Mars, that is the desert next to the Nile River, and you can see these features. These are dry river valleys. They have probably formed over thousands of years with the occasional rainfall, strong rainfalls, and erosion that takes place then. And if you look at the bottom of the valleys, you can see that they have a relatively smooth surface, and these are smaller particles that are deposited there. And this is probably also a dust source. I have not verified it whether this feature is particularly the dust source, but this is, for instance, this type of features that can produce dust when there's strong winds and high friction velocity, which can lead to dust emission. So now I'm going to talk a little bit why the mineral composition of dust is important. Dust models have been developed for 20 years, about 20 years in global models, and traditionally global dust models have used globally uniform dust properties, radiative chemical and physical properties. with different size distribution of the dust, but no further differentiation with respect to the dust properties. So that has limitations. We have learned a lot by this approach about the importance of dust in the Earth system, the radiative impact of dust compared to other aerosols, and the variability of dust. But it has limitations for some reasons. For instance, the single scattering albedo of dust particles depends on the mineral composition, particularly on the mass fraction of hematite or glycite. This figure illustrates this. This is from a paper by Moosmiller, where they measured the single scattering. They took soil samples from different regions in the Sahel and other places in North Africa, and then they measured the iron content in this soil sample and the single scattering albedo. And what they found is a very clear dependence of the single scattering albedo on the iron content. So Mali is this dust sample which has relatively high iron content, and the single scattering albedo goes down to 0.85 in their measurements. So this has these differences in the single scattering albedo, which varies with mineral composition and the geographical location, which determines the mineral composition. This is an important aspect for the role of dust as a component that drives climate. The aerosol forcing, so the radiative impact of dust and the response of clouds and atmospheric circulation to the forcing depends on the single scattering albedo. I illustrate this here with a paper published a few years ago by us, where we did some idealized experiments. In one experiment, we assumed mostly reflecting dust, and in the other experiment, we assumed more absorbing dust, and that shows the zonal average over between 20 degrees east and 85 degrees east, so it covers northern Africa, somewhat east of it, and in summer. And the shadings show the vertical velocity, and then the contour lines, the specific humidity, and we also show the temperature. So what we found is that for highly reflecting dust, the aerosol forcing is, when the aerosol forcing is co-located with moisture convergence, then the highly reflecting dust leads to a decrease in the Hadley-Walker circulation. And with more absorbing dust, it increases the moisture convergence, and so the dust acts as diabatic heating source, and it increases the Hadley-Walker circulation. So this we take as an indicator that we actually need to know the mineral composition of dust aerosols to properly simulate the global circulation and cloud cover changes which are related to that, and the response of the climate system. So heterogeneous chemistry, I had already mentioned the importance of heterogeneous chemistry. So dust is also influenced by the mineral composition, since different minerals have different uptake probabilities. Then some dust particles are able to some minerals are able to uptake water, particularly smectite and illite, which makes them potentially important for us cloud condensation nuclei, and I also talked about the importance of dust for ice nucleation, and the ice nucleating properties very much depend on the mineral composition. Recently, Atkinson have recently published a paper about the role of potassium feldspar as most important ice-forming nuclei. And also the fertilization of phytoplankton in the oceans is linked to the availability of soluble iron, and different mineral types contain different iron content, either structural iron, for instance in eelite, or as iron or iron oxide crystals, which are also found in dust. So for this, we also have to know the mineral composition. So how do we approach the modeling the mineral composition of dust aerosols? We need different data sets. One data set is what we call the mean mineralogical table, which basically assigns a mean mineral composition to different types of dry soils. Actually 28 arid soil types. This table was compiled in 1999. There's an update by Nikovic in 2012. And what I want to point out in this table, with respect to this table, is that it provides the mineral composition for two size classes, one for the clay fraction that is up to 2 micrometers, and one for the silt fraction, which is up between 2 to 50 micrometers. And one important feature is that, so we have 8 minerals: eelite, carnite, smectite, calcite, quartz, feldspar, hematite, and gypsum. But one important feature of the table is that some minerals are only found in the clay fraction, eelite, carnite, and smectite, and some minerals are only found in the silt fraction, like feldspar and gypsum. The absence of eelite, carnite, and smectite in the silt fraction can be attributed to the fact that these measurements of the mineral composition are based on a technique that is called wet sieving. I'm going to talk a little bit more about this later. The absence of feldspar and gypsum in the clay fraction, I don't really have an explanation for that, because that doesn't have anything to do with wet sieving. That I suspect that was because of a lack of measurements. So we have this table which assigns the mineral composition to the different soil types. Then we have the digital soil type of the world, a geographical distribution of the different soil types, of all different soil types that have been defined, including the arid soil types. And the third data set are the soil textures. For one, the different soil texture types, also the geographical distribution. And then for each soil texture type, we have a proportion of the fraction of sand, silt, or clay within for the soil texture type, and which we need to know for our mineral composition. So when we put this information together, these different data sets, then we can derive a geographical distribution of the mineral fractions in soil for clay and silt. And since we want to simulate the aerosol mineral fractions, well, the most simple approach for this may be just to assume that the mineral fractions in soil translate 1-to-1 into the mineral fractions of the dust aerosols. Then we have the dust emission flux at a geographical location for clay and silt, and then we multiply it with the composition, and then we get the partitioning of the dust emission flux or the mineral emission flux at the location for clay and silt. Now, dust emission itself is a little bit more complicated process. It's not just as simple that it translates 1-to-1. We have various physical processes that lead to dust emission. We have aerodynamic entrainment, for instance. That process is most important for larger particles, which is by the kinetic energy of the wind is sufficient to uplift these particles, and they are emitted into the atmosphere. this mechanism doesn't work as well for smaller particles because of the cohesion forces per surface area are too large. For wind, the kinetic energy of the wind is not sufficient to uplift these smaller particles because of that to overcome these forces. But the smaller particles are emitted by what is called saltation bombardment. So larger particles are uplifted, so you have the impact on the smaller particles on the soil, on the parent soil, and then the energy is sufficient to release the smaller particles. Or another process, if we have an aggregate in the soil that is uplifted and it splinters into smaller particles and which are emitted. There's another aspect here, which I already mentioned, that is that soil scientists, when they measure soils, the soil textures or the mineral composition, they often do this based on using wet sieve soil. What they do is they take a soil sample, and then the soil sample is washed through a series of sieves, and then you get a size distribution of the soil, and also mineral composition is measured based on this. And the problem with this approach is that it basically destroys the aggregates of the parent soils, while in real dust that is emitted is a mixture of aggregates and individual particles, which is not reproduced by this methodology. So what the consequence of this is that the wet sieved soil texture fractions do not sufficiently well represent the size distribution of the eroded soils in nature. They also are not a good representation of the suspended dust size distribution, and the wet sieve clay and silt mineral fractions are not a good representation of the mineral fractions of the suspended dust aerosols. So we have not been satisfied with the simple approach, therefore, and so we thought we want to approach it a little bit differently. Oh yes, I forgot about that. There's also evidence for measurements that what we are thinking that the wet sieve soil is not a sufficient basis for simulating dust aerosols or the mineral composition of dust aerosols. There's evidence for measurements. This is from these measurements that these are the volume size distributions of different minerals we have derived from measurements of the surface concentration of dust at Tinfoug, Morocco. This is a very unique data set where Canla et al. They measured the relative composition of the dust, the mineral composition of dust for 10 different size bins. And they also provide a number distribution. With this information, we can derive the volume size distribution for the minerals. And as you can see is that, for instance, for eelite, carnite, the clay minerals, which are absent in the silt size range, actually most of the mass, of the measured mass of these minerals is found in size range larger than 2 micrometers. The measurements go from 0.1 to 250 micrometers. And so that is a strong contradiction to the mean mineralogical table. And for quartz, which has most of the fractions, the mean mineralogical table also in the silt size range, but for quartz, what this very distinctive feature is that most of the mass is really at very large sizes, and it becomes the dominant mineral only in sizes around 50 micrometers and larger. Okay, so I said we are not satisfied with the simple approach because of these problems with the data, with the wet sieve data, and we said we are going to try something else. Our approach is based on brittle fragmentation theory that was developed by Jasper Koch and published in PNAS 2011. And we combine this brittle fragmentation theory with an empirical mineral size distribution, the one from derived from Candler, to derive the size-dependent mineral fractions of the emitted dust aerosols. So just in short, the brittle fragmentation theory is based on the hypothesis that dust aggregates behave in the siltation regime like brittle material. Then the size, then you can assume a specific size distribution, which follows a power law for the number, and combined, so the power law depends on the inverse power of, depends on power of 2, and combined with a cutoff scale that describes the maximum propagation length of cracks in the aggregates. And another component of this approach is reaggregation of the wet-sieved soils based on the measured wet-sieved soils, which is based on the assumption that, or the heuristic approach, that dust aggregates of a particle diameter can only be composed of particles smaller of this particle diameter. And then it is hypothesized that the number density of the emitted dust aerosols for this particle size of the aggregate is proportional to the integrated dust mass in soil up to this particle size. So if you double the dust mass in soil, then you double the number of the emitted particle at this specific size. So when we assume a log normal distribution for the fully dispersed soil, then we can derive a size distribution for the emitted dust aggregates by combining the two relations 1 and 2. So what we get then is something like that. If the ochre colored curve is the size distribution of the dispersed soil, by reaggregation we get a new size distribution for the emitted dust aerosols, which peaks at larger sizes and basically shifts mass from the clay range into the silt size range, in short. So that is for Jasper Koch developed this for dust in general, not for different minerals, and we modified this approach for the different minerals. So we reaggregate the clay minerals from the clay size range into the silt size range. I'm not going to go into details, so that is published, and anyone who's interested can read this. And there's a caveat with coming with this approach. The brittle fragmentation theory is only valid for dust emission in the siltation regime. But as I showed from the distribution, from the data by Candler, that actually a lot of the dust mass is being found, of the emitted dust mass, or measured dust, near sources at least, at much larger size ranges. So we wanted to take this into account too. So we augmented the size, the clay to silt ratio, which we derive from brittle fragmentation theory, by assuming that the empirical size distribution, volume size distribution for the individual minerals in the silt size range is sufficient, or if that we assume this one is globally uniform, and then we can use this size distribution to partition the mass in the silt size range over the different size bits we simulate, and we get, this is basically the same what I showed before, just projected onto our model size bins, with most of the mass of eelite, kaolinite, Smectite is found in the silt size range, in the bins of the silt size range, which starts with the second one. And quartz, the quartz distribution is very steep, with most of the mass in the larger size bins. So we implemented this approach in our Earth system model, which is NASA GIS model E2. And so as Earth system model, that's what we describe as a model that includes all relevant processes, the energy and mass fluxes between the components of the planet, the atmosphere, ocean, land, cryosphere, biosphere, to simulate the climate variability in response to changing boundary conditions by external drivers. For instance, forcing by solar variability, anthropogenic greenhouse gases, etc., or due to enforced internal variability. So for our experiments, we didn't use all components. We only used the atmospheric component and prescribed the lower boundary conditions. The resolution of the atmospheric model is 2 times 2.5 degrees latitude by longitude. This is about 250 kilometers resolution, so it's relatively coarse resolution nowadays. We also have versions of the model, cube sphere versions of the model, with a higher resolution, but we didn't use that one in our simulations. The model has 40 vertical layers and simulates up to 0.1 hectopascal. That is up to into the mesosphere. And the model also simulates all different types of aerosols, that is solid or liquid particles in the atmosphere, which influence the radiation fluxes, clouds, and atmospheric chemistry. In general, we only use mineral dust in our case, since we were specifically interested in the simulation of the mineral fractions. And soil dust, of course, is a major aerosol in our model, and it covers we have 5 size bins for dust, covering 0.1 to 32 micrometers in diameter. So here I'm showing how the simulated dust looks like. That shows the annual average of the simulation. We did a 10-year simulation. This is a surface concentration of the total dust. So we have the highest concentration near the dust sources around North Africa and the Arabian Peninsula and Central Asia, also in Australia. And then the dust concentration decreases with distance from the sources, because the largest particles fall out fastest. And so the smallest particles are transported to more remote regions. And if we partition the total for the total dust mass for the clay size range and for the silt size range, then one can see that most of the dust mass, simulated dust mass, is found in the silt size range. So that looks very similar to the traditional approach, since it's just the integrated dust over all mineral types. If you look at the simulated mineral fractions of the dust, one can see that these different minerals, the mineral fraction have very distinctive geographical features. For instance, we have quartz, which has the highest fraction near the deserts, which have a relatively high quartz fraction in the soil. Near the deserts, and for instance in North Africa, and other minerals show a different geographical distribution, like aelite, which has largest fractions in the middle and high latitudes. Smectite is similar to the distribution of smectite is similar to aelite, since both minerals are closely connected in the weathering process and often are being found as interstratified layers. If we compare it, for instance, to kaolinite, then we get a very different distribution. We have a maximum of the kaolinite in tropical regions, particularly in the Sahel region. This is related to the weathering process too. Kaolinite and illite are formed from the tectosilicates, and depending on the conditions, the Sahel region is very humid and warm, and that prefers the formation or the formation of kaolinite is preferred in these kind of conditions. Then iron oxide has also maximum in the tropical regions. Iron oxide is basically the end product of the weathering process. It's rust. Then the forming on the mineral particles first are small iron oxide particles on illite, for instance, and then it grows in time, and so the soils with the largest iron oxide content are the soils where the weathering process has progressed most. So that is what we simulate with our model. We also took into consideration iron oxide accretions with other minerals. The rationale for that is following. The minerals have relatively similar densities, except for iron oxides, where the density of iron oxide is about twice as high as for the other minerals. So we had a thought about how is this iron oxide transported to remote regions, because it's also measured in remote regions. For the other minerals, we could assume that for the transport that they externally mix because of their similar densities. We could not do that for the iron oxides. So we made a relatively simple assumptions. We assumed that iron oxide, the probability to find pure iron oxide crystals in dust aerosols is highest in the regions where you have the most iron oxide in soil, because weathering process has progressed most there. So we assumed that, and then we partitioned the iron oxide among the other minerals. So we did calculate this in the GCM, and so what we get is basically that we have accretions of iron oxides with each of the other minerals, to then a fraction of non-accreted iron oxides in the model, and also non-accreted other minerals. This is how it looks like. These are what I'm showing you. We didn't know what comes out of this, so how much of the iron oxide will be.
So for how long was the model run, and is there precipitation in the model?
We run the model for 10 years.
And the precipitation washes down?
Yes, we have the model. We have wet deposition. We have wet deposition, turbulence, deposition, gravitational settling. So all these deposition processes are included.
But the sources are constant?
The sources are constant, yeah. We assume that in the time frame which we consider, that there's no variation in the composition of the mineral composition of the sources.
So
we also
the sources are damp where precipitation occurs?
Yes, for dust emission, we assume there are constraints for dust emission. So dust emission takes place where the soil is dry. So we have our dust emission depends on the threshold, wind speed threshold, and which is modified with soil moisture. So the higher the soil moisture is, the higher the threshold for dust emission is. So what we get when we do this approach, what we get is basically that almost all of the iron oxide is accreted, only more than 90% on average, and only in the region where we have a high iron oxide content, there is a higher fraction of pure crystalline iron transported. If we look at the total dust mass, then about 35% of the total dust mass has iron oxide accretions. We don't know whether that is right. We don't have any data, so that is really, we have a heuristic approach. We have to make an assumption, but currently we don't have any way to constrain this, and so it's probably subject to revision at a later point. So we also did some evaluation of our simulated mineral fractions. We compiled from about 60 references in the literature the measured mineral fractions. It covers about the time range from the 60s to present day to get a sufficient number of measurements which we can compare with our simulations. Now, it said our model simulations over 10 years, and our model output is monthly average model output. So then the question is how to compare the measurements to the model climatology. It's a challenge. I think we found a sufficient approach, particularly since we were not interested in very sophisticated statistics. We want to see whether we can have robust improvements in the model. So for that, I think that these measurements are sufficient, but the measurements have limitations. They are mostly campaign data or from cruises. They have small sampling sizes, and there are possible biases depending on the methods. They have changed over time. For details, I refer to the second paper, which we published about this. Also, we also have a supplemental material where we describe these different data we used. So this displays the measurements. So as you can see, we have relatively abundant measurements around the major dust source region of North Africa, Mediterranean, also in near Saudi Arabia and Saudi Arabian Peninsula. Not so many measurements in the dust source, where the dust sources are actually. We have some measurements in the Pacific, so we can have measurements about the mineral composition of dust that has been transported to more remote regions. The southern hemisphere is underrepresented in the measurements. So we only have actually 2 measurements that are related to southern hemisphere dust sources, like that one is on Amsterdam Island, French territory, and another one is measurement or dust that has fallen in snow and where snow was analyzed in New Zealand. Okay, so we only a few data which we have actually are detailed enough that they provide measurements for individual months and also resolved for different sizes. But these few measurements actually show something very interesting. I mean, it's something that we could expect from our approach, but it shows in the measurements that I think that we are on the right path here. These measurements are from the Pacific, so it's dust that has been transported after a few days of transport. And these are the error bars, the dots in the error bars show the measurements, and then we compare this with two simulations. One is a simulation based on what I call the simple approach, and the other one with the dashed line is our aerosol mineral fraction method, the new approach. And as expected, the simple approach cannot simulate the illite or smectite or also kaolinite in the silt size range, but actually these minerals are measured in the silt size range. And our simulations with new approach shows actually reasonable agreement with these measurements, and we did not tune this or anyway. That came out just like this. Well, the measurements have also a large uncertainty range, some of them. This is due to the small sampling size, so you could argue it's always in agreement. But it's not always the case, so the measurements also show a good agreement where the error bars are smaller with our simulation. Or if you look at quartz, that is also an interesting feature, that for the simple approach, the simulated quartz in the cell size range is way overestimated. But if we use our approach with the reaggregation of the clay minerals into the cell size range, then we can reproduce the simulated quartz fraction much better than with the simple approach. And that is because of the reaggregation of the clay minerals, the quartz fraction, because I'm showing fractions, the quartz fraction is reduced to a smaller value. Okay, so if I drop the condition that I use data for individual months, but it can include some more data where we have annual averages of measurements or multi-month measurements, and we compare again. I show again the simulated mineral fractions in cell size range, and show it for elite, kaolinite, and for quartz, and for elite and smectite as interstratified minerals. The upper row shows the simulation for the simple approach. The middle row shows the simulation for our new approach, and what I just showed for these few measurements in the Pacific is corroborated also for the other measurements. The simple approach, of course, cannot reproduce at all the measurements, but the measurements all show mineral fractions regardless what region we look at. The measurements show mineral fractions in the cell size range for elite, kaolinite, and smectite, and quartz is overestimated generally. But if we use our new approach, we get a strong improvement in the results. So we are able to simulate the mineral fractions of elite, kaolinite, and smectite. We can reduce the overestimation of quartz. We are not perfect. There are deficiencies in the model, but it's a good progress compared to the simple approach. The third row shows the sensitivity experiment, where we assumed the size distribution we used for brittle fragmentation theory and augmentation with Candler data, but we did not allow any reaggregation of the clay minerals into the cell size range. And if you don't allow any reaggregation of the clay minerals into the cell size range, we are back to not being able to simulate the elite, kaolinite, and smectite in the cell size range, but also we are also back to the strong overestimation of quartz in the cell size range. Okay, so that's so far on our work on on our new mineral model. Now a little bit about my playing with ice nucleation. Very few attempts have been made to calculate ice-forming nuclei abundance from mineral species simulated with a global model. There is a study by Hose in 2008 who used kaolinite on elite montmorillonite. And then there is a study I already mentioned by Atkinson, who found the importance of potassium feldspar for ice nucleation. What I was reading the study, and what I noticed is that they, like Hose, use this approach, what I call the simple approach. And I was reading the study, so that is results they got. This is the feldspar mass fraction they simulated. This is the ice nuclei concentration they got from this, and this is the tsunami cross section of the ice nucleation concentration, which they calculated at fixed temperatures. So I was reading this paper and I was thinking by myself, well, so they have used this simple approach. What if we try this with our approach? How will the results differ? Because our approach has different size distribution of the minerals. So to do that, I designed 4 experiments. One is a baseline experiment, which is basically the same setup as in the Atkinson et al. Study, an active sites parameterization with nucleation densities at fixed temperatures, That was their assumption, and the mineral fractions in soil were projected onto the Aerocom dust emission. Aerocom is a project where it's an aerosol model intercomparison project where groups from all over the world compare simulations based on standardized boundary conditions and emissions, and also a size distribution. So they took the size distribution from this project and projected the mineral fractions from in soil onto the size distribution. Then the second experiment is one where we choose our approach as I have just described. Then I designed a third experiment. Since we both modify size distribution of the total dust and the mineral composition, I designed a third experiment where I assumed the Aerocom dust emission, then I just projected our mineral fractions from our method onto the size distribution as a kind of intermediate experiments between the first two. And then a fourth experiment, which I call AMF feldspar, is motivated by the fact that the data which we used provided by Candler for the relative volume fractions to get the volume fractions for feldspar and the different size bins, Candler made some specific assumptions which in their approach to derive these volume fractions for feldspar, which probably led to an error in the size distribution of feldspar, that the size distribution of feldspar peaks together with the together with the phyllosilicates, elite and kaolinite, but in the nature, the size distribution of feldspar probably peaks at larger sizes than that. So I thought I would have to study how sensitive our results are to a modification of the size distribution in feldspar, and I just assume for the fourth experiment as an extreme case that the feldspar size distribution follows the size distribution of quartz. So this figure displays the normalized emitted mass size distribution for the four simulation. I grouped the Aerocom simulation stations together, and then the one based on our new method, or based with our new method and the sensitivity experiment. So we see for total dust, the distribution for total dust for the four experiments. They are the same for the two Aerocom simulations, but what we can see, what I already talked about for the simple approach chosen by Atkinson, all the dust, all the mass of elite and kaolinite and smectite is found in the clay size range. There's no mass in the silt size range. We have when we project our mineral composition onto the Aerocom size distribution, then we of course get also mass in the silt size range, but this mass differs, the size distribution differs from our approach. In our approach, the size distribution peaks at large sizes compared to the Aerocom approach. And for the same for quartz, we have a larger, most of the dust quartz mass peaks in the largest size range at which we look here. So first I looked whether we can reproduce the results by Atkinson, and we basically can reproduce it. This is the dust number concentration in the upper left panel, which we simulated, the feldspar mass fraction, and then the ice from a nuclear concentration. One is external mixture assumption, the other one is internal mixture assumption, but they don't differ so much. So we generally can reproduce the magnitude and the pattern that Atkinson et al. Got, which is good news. There are some differences, but they are still different models, so we cannot expect identical results. And now I'm just jumping forward to the results with respect to the different size distributions we assume for the mineral for feldspar And there's also modification here. I calculated, since I was interested in more the realistic world conditions in the world, I calculated the IFN concentrations for the thermodynamic conditions, how they vary in the atmosphere, with varying temperature. The active sites approach only depends on the temperature. So we get, this is a baseline experiment that is basically the Atkinson experiment, but with varying temperature. So we get maximum of the ice forming nuclei concentration about at around 400 hectopascal and mostly in the northern hemisphere, because most of the dust mass is feldspar mass is concentrated in the northern hemisphere. But if we use our method, we get a very different result. We actually get a reduction in the northern hemisphere. I cannot really explain yet this increase in the southern hemisphere in our experiment. It may be related to a larger mass of clay in of feldspar in the clay size range. Our simulation. But if we move, or if we look at the sensitivity experiment with feldspar, where we assume a steeper size distribution for feldspar, then there is a even stronger reduction of the ice forming nuclei. So the preliminary conclusion is that the size distribution is important for calculating ice forming nuclei, and that is an additional source of uncertainty. So I think I have a few more minutes to talk about our grand plan. So we have, what do we want to do with the minerals in our model? For now, we have simulated. We simulate the soil dust, the mineral dust cycle. So we have the dust emission, which depends on the wind speed, 5 size bins, and 8 minerals with accretions, and transport and deposition. But what we want to additionally include in our model is that we want to simulate the heterogeneous chemistry of the minerals with precursor gases, with mineral-dependent reaction probabilities. We want to study the radiative forcing with minerals depending on the refractive indexes of the minerals, which vary with the mineral type. We want to calculate minerals as CCN and ice-forming nuclei with mineral-dependent activation. And we also working on, this also a work in progress, that we use the minerals as pools for processing of bioavailable iron, which then for fertilization of phytoplankton in the ocean and calculating the carbon cycle in the ocean. So that is generally our grand plan. Okay, summary. So dust is an important aerosol, which is involved in different physical and chemical processes in the Earth system. Using one type of dust in modeling has provided important knowledge over the last 20 years about the role of dust, but it comes with limitations. I have talked about these limitations. To overcome these limitations, the mineral composition of dust needs to be simulated. We have developed an improved approach by applying Claquin's mean mineralogical table in combination with brittle fragmentation theory and measurements to derive the aerosol size distributions, or the dust aerosol size distribution at emission for each mineral type. We simulate emission, transport, and deposition of a mixture of non-accreted minerals and accretions of iron oxides with each of the other minerals in the clay and silt size bins. And the comparison between the SMF method and the AMF method shows a robust improvement for latter, although some deficiencies remain. Also about the mean mineralogical table, they are nevertheless very useful data So it's nothing to throw away, despite of the wet sealing issues. They just have to be properly applied to derive the mineral fractions of the dust aerosols. And well, the simulation of the minerals opens the door to many interesting applications. I just showed an example with the ice nucleation. Thank you.
All right, thank you, Jan. A few minutes for questions. Yeah.
So in the table, the chemical composition that you showed in the beginning.
Yes, the mineral fractions.
Yeah, so there is no variation. I mean, so
Yeah.
these are just numbers.
Yeah.
So obviously in nature there is a lot of variability. So how much, like, how widely sampled, like, how representative are these, and what is the variability that you expect?
Well, the table provides standard deviations too, but the standard deviations, it's true, that's an issue with the table. It's the only data we have that is the mean mineral composition for the different soil types, because that is an assumption. There are probably also variations within the soil type. So that we don't have any data about that, what the variations actually are. I think the whole table is based on maybe 200 measurements or so altogether, but then it depends on the mineral type. Some mineral types are not well represented in there. Others are much better represented in the soils. So yes, there is probably a lot of variation in these standard deviations. The standard deviations is based on the variation of the measurements, which is the standard deviation in the second row to each of the soils. So standard deviation is about sometimes as large as the mean value, as you can see. That maybe this, because we assume this mean value for the soil types, that can be also one of the reasons. It's one of the source of uncertainty. It can be one of the reasons why we see certain deficiencies in the model. For instance, we have an underestimation of kaolinite on average, and
also see when you compare
overestimation
the model with the observations in the Pacific,
yeah.
and in the data and the observation there is a lot of variation.
Yeah.
But the model doesn't show variation. So this is one source.
Yeah, the model doesn't show these.
And the other thing
yeah.
I would like to describe, so if for realistic simulation we should know that dust emission or mineral dust emissions is sensitive to surface velocity, wind velocity.
Yes.
Which then introduces a lot of variability.
Yes.
So you have this. So
yeah.
I think
we have
should be included like
for dust emission we assume a probability distribution of dust emission, where the dust emission depends on when the probability of the distribution describes the emission flux as a function of the wind speed, and then when it exceeds a certain wind speed, then this area is basically the emitted dust mass. So we take into consideration certain subgrid scale processes for this to calculate the dust emission. So we take this to a degree into account in our dust emission.
Yeah, it was very good to see you move from Africa to North Amazonia.
Yeah.
It's very important for climate.
Yes.
So have you done climate change experiments and see if those characteristics will not change?
Well, we haven't particularly done climate change experiments to see how the dust changes. They have been done in the literature, but it's highly uncertain. So we cannot really say how total dust emission will change in the future, and not at this stage. So I would not be able to give you a prediction about that.
My point is that because in the future change, a model will be shift of jets.
Yeah.
With main currents to the north.
Yeah.
And in that case, may miss Amazonia, and that would have a profound effect on bioavailable, right? Because iron is
Phosphorus.
right.
Yeah.
emitted. You talked about the minerals. Do you have any idea if there's any organic matter associated with this dust?
Well,
usually from soil there should be, I don't know, humic acids or something, this peat. You know, if you dig in a garden, you don't have only minerals.
Yeah.
I'm just wondering, is that going away from wet sieving, or
No.
why is that not included? Or
Well,
any idea?
these are different questions.
Yeah, I know.
This is more than one question.
Okay.
Wet sieving, yeah, the mineral fraction measurements are specifically for the mineral fraction measurements, but measurements of dust, you see in measurements of dust aerosols that there are also mixtures with organics. So they are there. It's just we just don't simulate it here. So we don't have this degree of complexity currently in the model to simulate mixtures with organics.
Yeah, I was just thinking about the effect of the aerosol direct effect. You mentioned the indices, refractive indices, and of course with organic matter that changes again.
Will
Maybe
change, yeah.
stronger UV absorbers and
Yeah.
need for more layer heating than without organic.
It also can change with aging.
Yeah. Okay. All right. If there are no other questions, then I thank Jan again for his nice talk, and let's meet at lunch. Oh, very tedious. Wow, that took a while. Now I see. Okay.